So we're starting limits. Okay, we're starting limits. Oh, what? This is so bad. Oh, all right. So in Math 31, so Math 31 is calculus, if you didn't know that, you should. We look at two fundamental concepts related to calculus, the slope of a tangent to the curve and the area under a curve. The area under a curve we're going to do last, and then the slope of a tangent we're going to do right away. And a lot of it is based actually on the slope of a tangent to a curve. That's why derivatives are found. So we'll also look at operations of differentiation and integration. So differentiation is next unit, integration is the last unit. Throughout the course, we'll apply these concepts in problem-solving application. Under the assumption that functions used are continuous, we explore what happens as you approach a value but never reach it. So that's what a limit is, as you're approaching a value but not specifically at that actual point, okay? A limit from the left and right, but as you're approaching the value. That's the hardest thing for people to grasp, is that a limit is not that value, it's what it approaches. We will look at the indeterminate form 0 over 0. So if when you fill into a limit, remember I told you how you'd fill into a limit? If you fill into a limit and you get 0 over 0, that's the indeterminate form, as this relates to limits and eventually discuss the formation of the derivative of a function. So when you get that 0 over 0, when you fill into a limit, the answer isn't just 0. If you get 0 over 2, then the answer would be 0. But if you get 0 over 0, that's an indeterminate form, and we're going to have to do something before actually filling into it, which will make sense in a little bit. So example 1, graph the function of f of x equals x squared plus 1 from -1 to -3 inclusive. So this is read the limit of, so this here, determine the limit. So it says the limit of x squared plus 1 as x approaches 2 from the left. This little negative sign after means from the left. If there was a plus sign behind it, it would mean from the right. Because every point on a graph can be approached from the left and from the right. This is your right, your left. Okay? So the value that the function approaches as we let x get sufficiently close to 2. So we get closer and closer to 2, but not necessarily touching 2. All right. So we can use a table of values and test this. So limits, the basic way that they figured out how to do limits was actually approaching from the left and approaching from the right, or wherever you're approaching from, and getting closer and closer to that value and plugging those values in for x and solving for y. So this one here, we want to look as from 2 from the left. Okay, from the left of 2 are all the numbers up to 2 from the left. So like 1.5, 1.9, 1.9999. Those are getting closer and closer to 2, but not touching 2, right? So what they did is they said, okay, well, I'll take this 1.5 and I'll plug it in. 1.5 squared plus 1 is 3.25. Then I plug in 1.9 because that's getting closer to 2 from the left, right? Plug that in. 1.9 squared plus 1 is 4.61. Then I plugged in 1.99, 1.999, 1.9999. Plug that in. Square it plus 1, and I get 4.999600001. What can I say that it's approaching? What value from the left? 5, right? And if we look here, if we actually drew the graph correctly, we could look from 2 and see what it's actually approaching. But because I didn't draw it with a scale, you don't know exactly where those ticks are, right? So you'd have to actually look at it on your calculator or sketch it with the points. So the value of a limit depends only on how the function behaves near the point in question and not on its value of at that point. Because a limit often is found at an asymptote or a point of discontinuity. So if I asked you at 2, and there was a point of discontinuity at 2, if I asked you at 2, what's the limit? Okay, you'd be like, nothing, it doesn't exist. So limits are what it approaches as you get close to that value. So even if that value at 2 didn't exist, it could have a limit. Okay? So we can write this as the value of f of x approaches 5. The limit as x approaches 2 from the left of x squared plus 1 equals 5. So you just write it like that. Now what if we approach it from the right? That's what this means, this little plus sign. Flip over. So from the right of 2, we could start at like 2.5 and we'd want to get closer and closer to 2, right? So from the left, we started at 1.5 and then we went to 1.999999999. We could have went to get closer and closer from the left. From the right, we can use 2.5, 2.1, 2.001, 2.0001. We could go 2.00000000001, and we'd be really close to 2, but not actually at 2, right? So what we do is we take this again, we plug it in for our x. So 2.5 squared plus 1 is 7.25. Plug in 2.0001, square it, plus 1 is 5.00400001. So once again, we're saying, actually, this is approaching 5 as well, right? So the limit as x approached 2 from the right was 5. If the limit from the left and the limit from the right are the same, then the limit at 2 exists at that value. So the limit as x approaches 2 of x squared plus 1, the limit exists and is 5. Because from the left and from the right, it both approached 5, then the limit at just 2, not from the right or left, but at 2 actually equals 5. And this will make more sense when I have a few where there's graphs are drawn and you'll be able to see from the left and right too, where there's holes, when it's not actually, when it doesn't work. When no sign is indicated, this means we are checking both from the left and the right to see if the limit exists in general. So in order to find this limit, if it's from a graph that's a piecewise graph, you'd actually have to look from the left, look from the right, see if it's the same value, and if it is, then that's what it is. Okay? So we're going to look at this one. Determine the limit as x approaches 2 of f of x. So what I told you before we even did any of this, I told you guys that the first thing you want to do is you always want to plug in this value first and see if it works, right? So that would be the first thing we do. So the limit as x approaches 2 of 3x squared minus x plus 4. What I can try first, the first thing I always try with a limit is taking that value at x and just plugging it in. If when I plug it in, I get a 0 in the denominator, that's a problem. Or if when I plug it in, I get a 0 in the numerator and denominator, then it's indeterminate and I have a problem. But if I plug it in and I don't have either of those problems with just a 0 in the bottom or 2 zeros, then I'm done. I have my answer. So I can just plug in 2 and I check that out first to see if it works. So I go 3 times 2 squared minus 2 plus 4. And I get 4 times 3, which is 12, plus 2, and it's 14. Now, what does this really mean? It does mean that there actually is a point at 214 on this graph, and that as I approach from the left and as I approach from the right, they both approach 14, okay? So you can fill it in. So for the most part, limits aren't too bad as long as they're continuous. If it's a continuous graph, you can always just plug in your value of x and get y. If it's not a continuous graph, so there's holes or there's asymptotes, that's when you have problems where you can't just fill it in, okay? So this is a parabola. Parabolas are continuous, so I would be able to just fill it in and get an answer. If it was a cubic function, they're continuous. I could just fill it in and get an answer. So as long as the graph is continuous and doesn't stop anywhere, has a domain of XER, I can just fill in. So because this function is continuous, it has no holes or breaks, we can simply evaluate it, evaluate f2 to determine the limit. Let's look at this one. Determine the limit as x approaches 3 of square root x minus 3. For this function, x has to be greater than or equal to 3, which you guys know. That's why we were doing all that review before, because you're reviewing all the basic stuff in order to do the new advanced limits and derivatives. So you know that x has to be greater than or equal to 3 because you can't have a negative under your square root sign, right? You can have a 0. You can have positive values, but you can't have a negative. So here we have to look from the left and from the right because this doesn't have a domain of XER, right? So The limit as x approaches 3 from the right, that's a plus sign, is 0. But it's not possible to find the limit as x approaches left from, or 3 from the left. Why? There's no graph. This graph is a radical graph. Let's do a table of values first. Let's put in 3, because it has to, I said it has to be greater than or equal to 3, right? If I put in 3, square root of 3 minus 3 is 0. So I have a point at 3 and 0. Let's put in 4. 4 minus 3 is 1. Square root of 1 is 1. So 4 and 1. Etc. Right? So from the right, this graph is approaching 0. From the left, there is no graph. Right? So I can't give what the limit is from the left because there is no graph from the left. Okay? So the overall limit doesn't exist. So I can say that then the limit as x approaches 3 of square root x minus 3 does not exist. So if from the left and the right they don't approach the same thing, it doesn't exist. What if I asked you for the limit at 4? The limit as x approaches 4. From the left, what is the limit as x approach 4? Give me. 1. It's approaching 1, right? From the right, what is the limit as x approaching 4? Give me. 1. So what's the limit as x approaches 4? 1, because they're the same. Okay? So if you get the same limit from the left and right, the limit at just that value exists, at that value. Next page. So here's where it gets a little bit, where you can kind of understand it a little better because it's drawn. Okay. So here's not a continuous graph, right? So there's going to be places where this limit does exist, where the limit doesn't exist, all that stuff. So we're going to look at this one. The limit as x approaches negative 3. So what I'm going to have to do is approach it from the left, approach it from the right, and see if I get the same value, right? So what's the limit as x approaches negative 3 from the left of f of x? So I approach negative 3 from the left. What y value am I going to? 0. I approach negative 3 from the right, so positive, of f of x. F of x being this function that's over here. From the right, what's it approaching? 0. So because they're approaching the same thing, I can say that the limit as x approaches negative 3 of f of x is 0. It's continuous at that point. It's continuous at 3, so it will be 0. The only time it's not, the limit of what the value is if from the left it approaches like 0 and then there's a break, and from the right it approaches 3, and there would be no limit, which will happen in a second. So what about at 0? At 0, from the left it's approaching what? Looks like 9. From the right, what's it approaching? 9. So I can say that the limit as x approaches 0 is 9. Now what about 2? 2 has a break. So I'm going to do the limit. I'm not going to do it there because it's not approved. The limit as x approaches 2 from the left of f of x. From the left, what is my y? It's approaching 5, right? The limit as x approaches 2 from the right of f of x equals what? From the left, what am I approaching? 4. What's the limit as x approaches 2? Does not exist, right? Because they don't approach the same thing. So here it's a good example of f of x is defined. F of x, I can give you a value at f of x, but the limit doesn't exist. If I said to you now, let's just as an aside, what if I said to you, well, what is f of 2? Because f of 2 actually exists. The limit at 2 does not exist. What is f of 2? Haley, what do you think? 5. Because it's the closed circle, right? This is an open circle, so it doesn't actually equal it there. So it's like a piecewise function, right? Where it didn't equal it here, but it came up close to it, so I drew an open circle, and it equaled it here, so I drew a closed circle. So f of 2 actually equals 5. The function exists at 2. The limit does not, because the limit is what it approaches. The limit is not the actual value itself. So sometimes you can have a function, but not a limit. Sometimes you can have a limit, but not a function. How does that work? Let's look at this one. I'm getting ahead of myself, but that's okay. Let's go down to this 9. Five, 6, 7. Where is it? 7, 6, 7, 8, 9. Ignore this. It's a typo. So at 9, from the left, what am I approaching? 4, right? From the right of 9, what am I approaching? 4. So what's the limit as x approaches 9? 4. Because from the left I approached 4, from the right I approached 4. So it's 4. What is f of 9? Does not exist. It's an open dot. There is no value at 9. So here's an example where the limit doesn't exist, but the function does, because f of 2 equals 5. And here's an example where the limit exists, but the function doesn't. Make sense? In general, a function is discontinuous if it has holes or breaks in it. It does not mean that the function is undefined at a certain value in all cases. The limit does not exist. We have to check how the function behaves around that value from both sides. You can't just say the limit doesn't exist because there's a hole, right? You have to see where it approaches from the left, you have to see where it approaches from the right, and then go from there. So I want to give you, show you a case where we have a spot that doesn't exist. So from grade 12, you guys remember this. You factor the top, you factor the bottom, and if something crossed off, you got a what? Point of discontinuity. How do we find the y value of that point of discontinuity? Remember? Okay. X can equal -2? Yeah. I get what you're saying. So then what is it when x can't equal -2? So you plug it into the one that you've simplified. So y equals -2 minus 2. So it's -4. So we actually have a point of discontinuity at -2 and -4. So that's this one here. And then the rest of your graph is drawn, right? Your graph is just this line, y equals x minus 2. And if you put it into your calculator at this point, if you put in y equals x minus 2, it's going to just draw a line without any problems, right? Because y equals x minus 2 doesn't have a point of discontinuity. You'd actually have to fill in your original, and it's going to draw the line y equals x minus 2 with a hole. But this, if I just plug this into my y equals in my calculator, it's just going to draw a straight line without any issues because it doesn't have any issues. It's the line y equals x minus 2. So you always have to put in the original if you're actually going to check it on your calculator. So there's that open hole again. So at f of -2, what is my y value? -4 on the point of discontinuity, right? But is there actually a value of the function itself, of this y function at 2? No, it doesn't exist. There's a hole there. we can find this y value, but remember we would have to actually do this. Y can't equal -4, right? That we actually have to have can't equal signs here because it doesn't equal -4. At -2 and -4, we have a hole. So our domain of this graph is x can't equal -2. Our range of this graph is y can't equal -4. Remember, that's all from grade 12. So f of -2 does not exist. However, the limit at -2 does exist, right? From the left, I'm approaching -4. From the right, I'm approaching -4. And if from the left and from the right, I approach the same thing, the limit exists at that value. Does this make sense? It's grasping around that the limit is not exactly what the value is. The limit is what it approaches. I feel like I'm directing an airplane or something. The emergency seats are here. So here is a partial graph. So what we've been given before up till now is I've given you graphs or equations, or when it was a piecewise function graph, it was drawn, okay? What happens if I give you the piecewise function graph, or not the graph, sorry, the equation of the graph? Do I have to draw the graph and then look at it that way? I shouldn't have to. I just have to see if the limit they're asking me about, if the value from the left and from the right is the same. Really, right? So on piecewise functions, 99.9% of the time, unless I'm being tricky, I'm going to ask you for the limit at the value they share, okay? Because that's where there's going to be possibly a discontinuous part of a graph, right? It's at the point where they share. It should be continuous all the way up to that point because there's nothing stopping it, right? Unless it was a rational graph embedded in a point. Then it just gets really ugly, but that can happen. So most of the time I'll ask you where the limit as x approaches the shared x value exists. So let's see if we can figure out the y values at them. So what do I have to do? I have to look at the limit as x approaches. So if I just ask you, I'm ADDing here for a second. If I just ask you where the limit as x approaches 1 exists, if I do this, you have to do this without me asking you. Because if you don't do this, I don't know if you're getting this right. Okay? So when it is a piecewise function graph, we have to do from the left and right, even if I just ask you from just the value. Okay? So from the right, which equation represents x from the right? From the right of 1, are all the values bigger, right? So which of those equations represents all the values bigger than 1? Top one or the bottom one? The bottom one? Yes, Zach. Good answer. Okay, so it's the bottom one. All right, so as x approaches 1 from the right, we're going to use this value because it's where we're greater than 1. So I just plug in 1 into this equation. I go 1 minus 1 squared plus 3, which is 0 squared plus 3. So as the limit as x approaches 1 from the right of f of x is 3. Now I'm hoping from the left it's 3 as well so that I have something when it approaches just 1. So now I have to try from the left. Which of these equations represents from the left? Seth? Which one represents from the left? The top. So we're going to plug into that one, the number 1. 2 times 1 plus 5. It's 7. Oh, no. So from the right, it's approaching 3, and from the left, it's approaching 7. Some people will tell me, well, it's approaching the same. No. From the right, it's approaching 3. From the left, it's approaching 7. Are they approaching the same thing? No. Is there a discontinuous part in this graph? Yes. So the limit at 1, what? Does not exist. Because from the right, it's approaching 3. From the right, it's approaching 3. From the left, it's approaching 7, and they do not approach the same thing, so it does not exist. this is just your little rule down here. If the limit as x approaches a from the left does not equal the limit as x approaches a from the right, this is supposed to be a plus sign even though it doesn't really look like it, then the limit as x approaches a does not exist. That is a rule. If, this is the funky calculus notation, if the limit as x approaches a from the left equals L, L being just a limit, whatever that value may be, 7, 10, -2, and the limit as x approaches a from the right also equals that, see, look, from both sides it equals it, then the limit as x approaches a equals L. So they're just writing this as one equation rather than two. They're saying if this approaches L and this approaches L, then they both approach L. Okay? It's just funky calculus notation. Okay, flip over. These are your basic properties of limits. So the limit of a constant times a function is the constant times the limit of the function. So these are just rules that you can use. They're not hard to understand, and I'm pretty sure if I didn't even give you these laws, you would be able to do it. Maybe the first one you wouldn't figure out right away. So if I do the limit as a constant times the function, I can bring the constant outside of the limit and then just do the limit at that function. Why would that be? Because the constant doesn't have a variable anyway, so no matter what value this a is, it's not going to change that constant because I'm not plugging anything into it. So I technically could take the constant right out and then find the limit of it. When it has an addition, you just find the limit of f of x plus the limit of g of x. You can do them separately. When it's multiplication, you can do them separately. When it's quotient, so division, you can do them separately. Difference, you can do them separately. And then this one is just saying that if I have a function to a power, I can actually just do the limit of that function, and then whatever that value is, I can raise it to the power. And then roots, you can do the same thing. You could do the limit of what's underneath a root and then root it if you want. Those are just your basic limit laws. Okay. Then last one. And then we have some ones that you're going to just write out and do. So, evaluating limits, substitution and algebraic manipulation. So, in many cases, the limit can be found by direct substitution. And to be honest, if I give you a direct substitution question on your guys' test, most of you will try and do a whole bunch of math to figure out the ways that you could tweak it so that you could fill it in when you could just fill it in the first place. You leave it blank and there's no answer and you can't figure it out because all I actually wanted you to do was just fill it in. So for this example, if I give something like this, people will be like, they'll like try and multiply by 2x squared minus 4x, do some sort of conjugate with x's, multiply them out, then they FOIL it, then they collect like terms, and then they fill it in usually, and then they get an answer. When in reality, they could have just went the limit as x approaches 3, 2 times, so, sorry, 2x squared plus 4x. When you substitute that value in, the limit, the word, the limit, goes away. So you don't write this. Oh, no. All right. All right. So the limit is x approaches 3 of 2x squared plus 4x. We can now just substitute it in. The moment you substitute that 3 in, the limit is x approaches 3. Disappears magically. So we get 3 squared plus 4 times 3. Basically, this is a reminder that you are going to somehow substitute that 3 in at some point. Okay? Once you've substituted it in, this limit is gone. So don't like carry the limit till the very end and then tell me that it equals this with a limit in it. It's gone once you substitute it in. So we get 2 times 9, which is 18, plus 12, which is 30. So we actually have the limit as x approaches 3 of 2x squared plus 4x equals 30. So the first thing we always try is direct substitution. However, if we do direct substitution and you get 0 over 0, I said to you, it's said to be indeterminate. Not undefined necessarily, indeterminate. Okay? So to determine the limit of an indeterminate case, we need to do some math. Generally, algebraic manipulation will allow us to determine that limit. So for this one, if I did the limit as x approached 2, it would give me a 0 down here and a 0 up here, which is a problem. So we do some math and see if we can figure that problem out. So what I can say to myself is, okay, that top is a difference of squares. So let's factor it. Because my issue right now is this 2 minus x on the bottom, right? If I plug the 2 in, I have a 0. That needs to go away. So we have the limit as x approaches 2. We still write it because we haven't filled it in. Until we substitute that 2 in, the limit as x approaches 2 keeps being rewritten. Root 4 is 2. Goes in the front of each blank. Root x squared is x, goes at the back. And then we do plus or minus sign in the middle. The reason why you do the positive and negative sign in the middle on a difference of squares is because if you wanted to FOIL that back, your two middle terms would be plus 2x and minus 2x, which would cancel them off, right? Which would get you just 4 minus x squared. If they're the same sign, then you would get a middle term, which we don't want, right? So that's why the difference of squares is always one positive and one negative. So those middle terms, when you FOIL, go away. On the bottom, we have 2 minus x. And now a whole bunch of happy people exist because you see that the bottom is going to go away. And this is where on the test question, you're like, I think I can get this one. I'm good. Okay? Now, do I have to manipulate it any more, or can I just direct substitute now? Just substitute because I have no issues anymore. So the limit goes away and I just direct substitute. So in for x, I put a 2. And it's 4. So the actual answer to this, the limit is x approaches 2, 4 minus x squared over 2 minus x equals 4. This next one, so we pushed big time in grade 10 and 11 and 12 that you can't have radicals in the denominator. You need to rationalize the denominator, get the radicals out. Well, sometimes in calculus, we actually rationalize the numerator so that we don't have to get rid of our issues on the denominator. So why is there an issue on the denominator here? X can't equal 0. I fill in a 0, do direct substitution, and I'm like, foiled, can't do it. So the only thing I can think that I could possibly do here is whenever it has a radical, you have to multiply by the conjugate. So whether it's on the top or the bottom, it doesn't matter. So multiplying by the conjugate means exact same, almost, but opposite sign. Okay? So the first term and the last term are the same, but you put the opposite sign of what's in here so that it gets rid of those middle terms. So we have 1 plus root x. 1 plus 3x. 1 plus root 1 plus 3x. This is huge. This next step is very, very, very big deal. Very, very big deal. You will FOIL whatever the radicals that are together. You will FOIL those ones together. But the top or the bottom, whichever one you would actually don't have the conjugates on, do not put them together. Why? I want this to go away. It is not my friend right now. It is ruining my math. I can't have an x on the bottom. It needs to go away. The only way I can get it to go away is cross off something on the top and on that has an x, and hopefully they'll go away, right? If you distribute this x into this over here, it is now embedded in there. You are not getting it back out unless you pull it back out and then you're back to where you were in the first place. So we want this to go away. So you don't want to stick it in with these ones and distribute it in and get it lost in there. You want to leave it out here. So we distribute the conjugates, but we always leave these separate, or you'll be sitting for a while trying to figure out what you should do next. So we do the limit as x approaches 0, and then we FOIL. 1 times 1, 1. 1 times root 1 plus 3x is root 1 plus 3x. 1 times negative 1 root 3x is negative root 1 plus 3x. This is why we do the conjugate, because these are going to go away, right? That's why you multiply by the opposite sign. And then negative 1 times positive 1 is negative. And what's root 1 plus 3x times root 1 plus 3x? 1 plus 3x. That's one thing that throws people off. If I give you this, if I go root 3 times root 3, you tell me it's root 9, or what's the answer? 3. What if I tell you root x times root x? It's root x squared, or x. So whenever you multiply two radicals that are the same together, the answer is just that number. Because you're going to square that, and then when you square root it, it just goes back to the same number you had before, right? So square root 1 plus 3x times square root 1 plus 3x is just 1 plus 3x. Where does the error happen? You forget to put the bracket, because that negative sign that's in front goes to the 1 and the 3x. And the bottom I do not put together. So I get the limit as x approaches 0 of 1 minus 1 minus 3x, x, and then 1 plus root 1 plus 3x. On the top, I'm just left with the limit as x approaches 0 of negative 3x over x times 1 plus root 1 plus 3x. And my x is gone. My issue is gone. I can now fill in 0 and be a happy person because I can find the limit. So once I get rid of my issue, I can do direct substitution. So now my limit word goes away, and I just fill in 0. So I get negative 3 over 1 plus root 1 plus 3 times 0. So it's going to be negative 3 over 1 plus root 4, or negative 3 over 1 plus 2, or negative 3 over 3, or negative 1. Yeah. Which one am I times by 0? Just checking if you're paying attention. That would totally be 1. You guys let me go so far. Obviously you weren't paying attention. Silly you. I'm lazy and I don't want to do 3 over negative 3 over 2. Much better, even though it's a fraction. Mine looked prettier. It was wrong, but it was a nicer answer, per se. Yeah. Okay, determine the limit. One. The limit as t approaches 0 of nothing.